Thanks for the introduction. And I'm Wenyao from SUNY Buffalo. Today I will talk about our work on screen exposure detection. And today we have been hearing excellent talk about how to improve our technologies and our digital work better. And also would like to talk about the problem we create. So right now we are entering the digital world and we interact with the digital work every day. The devices, as for input devices, we have computer interface. However, as for the output devices, and most of the time we still refer to screen. That's why once we interact with the digital world, we call it screen time. So what happened to screen time? So right now, adults on average will spend 10 hours and 38 minutes. Believe or not, this statistics by the psychologists and the educators. And it creates a lot of health problems like sleep and vision. And this is even more serious to our children, the next generation. Right now in US, the kids spend 6 years during the childhood in front of different kind of screens. And it's 8 hours per day. Literally, it's equal to attend second school. So right now we are facing a new childhood crisis, the screen time. The screen time is not just affect the psychology and the mental health issues and also bring some medicine challenges. There has been studies indicating the risk of ADHD among the pre-age children is associated with the more time screen. So what can we do to deal with the screen time overdose? Should we educate our kids no computer, no Wi-Fi, and no televisions? I don't think that's the right way to do because they are facing the digital world. They need to learn how to use this technology. And we cannot imagine anyone who have no idea about those technology during their childhood. So in this case, what can we do? So let's recall the examples of weight loss. So many studies have indicating continuous daily weighting is a good practice of weight loss. Regularly weighting ourselves can motivate us to adjust our lifestyle to the good, have a good diet and exercise habit. So this practice is driven by a very simple technology, a weight scale. So in order to control our time exposure to the screen, it's urgent need and that we have a skill to measure our screen time. Since last year, many smart device vendors start to have built-in functions to meter our screen time, but it is not good enough. First, it is not pervasive, and the second way, it is not personalized. We can look at the picture here. A group of students are watching computer, and where the owner of the computer may not be here, but still get the credit of screen time. And another possible solution is using the wearable camera to continuous log over life. However, it also has the drawbacks. The first, it has a computational challenging, how to reliable detect the screen and then decide whether it's on or not. It is a challenging computer vision problem. Secondly, it's gonna raise a lot of privacy issue, not only to the user, but also to the people surrounding the user. So here we have a goal, and we want to develop our wearable solutions to continuously monitor the screen exposure and in a pervasive way, in a privacy-preserving way, and most important, it should be low cost. That's why we introduced our solution, SpecEye. Actually, SpecEye, it is not a super resolution eye. It's like a wearable, nearsighted digital eye. Rather than look at the world in a super resolution, and we just tune it just enough information to detect the existence of the screen in front of the user. So how can we develop this solution? First, let's look at the relationship between the screen exposure and the light. We know once we look at the screen, then our eye gonna receive the light from the screen. And if we look like a closer look at the screen, the light from the screen, and compare it with other lighting source like sunshine or the reading bulb, we can see that the spectrum, the light spectrum of the screen is different. Take the blue band, light band as an example. We can see the characteristics, the shape of the spectrum are distinguishable. This motivate us to utilize the light spectrum as a way to detect if there is a screen or not. So let's look at our hardware solution. Before that, we would like to review a concept, photovoltaic effect. Photovoltaic effect is a widely known effect in the lighting theory, and there is a p-n junctions in the LED, and there is a famous example of using photoelectric effect and to make a light when we applied the voltage. And the photovoltaic effect is a reverse process. It means once upon exposure to the light, the voltage and current will be created on the p-n junction. So given this, we have been run a preliminary study to characterize the reaction of p-n junction to the screen exposure. So we impose the p-n junction prototype in front of we use LEDs, the RGB LED, and the solar cell, the p-n junction inside to build the prototype. And then we tested it on multiple different lighting conditions. And from the figures here, we can see once the p-n junction is facing the screen light, then there is a charging and discharging process, which is a photovoltaic effect. So based on this phenomenon, we would like to develop our technology, our solution. So here is our system concept. There are two parts on our system. The front end, which is a wearable, and the back end is a smartphone to process the spectrum data from the wearable devices. So first, let's look at how we build the hardware. So we employ ultralight hardware architecture, which includes a SoC microcontroller with a built-in Bluetooth, and we use 3 PA junctions in the RGB LED and one solar cell function sensor there. And the entire system is supported by the lithium batteries, and because this is a very low duty cycle sensing task, and the battery lifetime can last more than 30 hours. And the total weight of the wearable part is 50 grams. The size is 30 by 32 by 8 millimeter, and the entire prototype cost is less than $10. And in the SpecEye prototype, we have been implemented to be used on 2 different locations. One gonna be used as a badge, and the other one can click on our glass frame. The next part is about the smartphone software. In the smartphone software, the goal is to analyze the spectrum and detect if there is a screen. And there are 3 components. The PA effect modeling, which try to understand the charge and discharge process of p-n junction once facing the light, and a discharge pattern recognition, and a screen detection algorithm. So first, let's look at the p-n effect modeling. We know when the p-n junction is in front of a lighting source, it's gonna get charged. And here is the formula to model the charging process. And we're gonna model the voltage and in real time and the time to charge and discharge. After we get the measure of the p-n junction, the voltage on the p-n junctions, we're gonna analyze the data to detect that there is specific features related to the screen exposure. Particularly, we're gonna extract the signals in the discharge part and compare it and use a template-based approach and see if there is a possibility to impose to a screen. And here from the features illustration, we can see the discharge pattern shows different features upon the screen exposure. And the last part is the screen detection algorithm. And the input is the features from the p-n junction discharge pattern. And it employs a tree-like structure, which has two levels cascaded SVM. And the kernel function used here is the Gaussian radian basis. Last but not the least, we also develop a smartphone-based UI to provide the user the feedback. One is the real-time feedback to see how much the lighting and what's the status of screen exposure. The other one is more like the live log to get to know the statistics of the screen exposure. So those are the all the technical discussion parts. And let's lay back and enjoying our video demo. Get start. So this shows there should be voice, and because of no voice, I'm gonna introduce. So here is shows how we provide the feedback, and we can analyze the types of the screen exposure, like how much time we watch TV, play video games, smartphone, and etc. And this can drive the different applications like eye protection, obesity control, and addiction control of network and the smartphone. So here we can see once the user in front of the screen, and it's gonna detect once it's take off, then there's no detection. Once you look at the smartphone, it can detect the screen again. And also, the SpecEye can detect the different size of the screens to understand the user behavior of the screen use. And also, it can work under different lighting conditions. We can see once the the environmental light is dimmed, and we still can, and our SpecEye can still detect the existence of the screen. So here is our video demo, and we would like to go to a little bit of detail, see how we validate and quantify the performance. So in this study, we use, first part is a controlled study. We use 51 displays, including 7 different types, the TV, the desktop, laptop, and smartphone. The screen size is ranging from 3.5 inch to 70 inch. And also, we conduct a study in 43 different locations, including 16 indoor, 14 semi-indoor, and 13 outdoor sites. First, let's look at the screen detection accuracy. And from this PR curve, we can see the accuracy of the SpecEye is very high under those scenarios, over 98%. And particularly once we analyze the equal error rate, we can see the false positive and the false negative are really balanced. And also it shows over over LED plus the solar cell solutions outperformed with other kind of lighting sensor combined. And the next part is about the screen lightness conditions test. In order to test the robustness on different lighting conditions, we dim the screen brightness from 100% until 20%, and the SpecEye still provides a stable detection rate over 97%. And also we test how it works with different distance and reasonable reading distance, and also the orientations. So from the accuracy, and we can see until 30 degree, and our SpecEye still can provide a stable screen detection performance. And also we conduct longitudinal study in the ecological environment to see how it works in the real world. So here is the experimental setup. We have 5 volunteers. It is 30 days long from 8 a.m. to 8 p.m. And we use a wearable live log camera to get the ground truth. And when we compare the ground truth using camera and our SpecEye, the agreement between them is 82 to 85%. Still pretty stable and accurate. And the very last, I would like to discuss the limitations. So privacy is very important in the screen detection. And in order to meet that goal, we have been utilized the minimal sensors, provide and acquire the minimal information for the screen exposure detection. However, we are not sure whether those minimal really means private. For example, in the example of compressed sensing, it has been proved a single pixel camera with a few samples, it is still possible to reconstruct a picture. So it is unknown whether we utilize a PN junction based sensor still could the hackers or malicious users cannot reconstruct the scene of the screen. And the second possible limitation is in the future, we're gonna have a different lighting source in our future screen technologies, like a quantum lighting. And once the lighting source changed, the performance of the SpecEye is unknown because it's based on the theory of the photovoltaic effect. So here is a summary and takeaway message. So SpecEye is a wearable system for the exposure detection. It is pervasive, it is low cost, and privacy preserving. And the technology here we utilize is a PN junction and the photovoltaic effect modeling, and which can achieve a high detection accuracy. We validate and evaluate the system performance on different conditions in a longitudinal study. Okay, so that's all my presentation. Thanks for your attention.